Hello gentlemen, welcome to our video on weak acids. This is section 6 from chapter 16. Now most acidic substances are weak acids. They run the acid world. And to be a weak acid, we define it as an acid that partially ionizes in solution. Strong acids completely ionize in solution. The equilibrium constant for the ionization reactions is used to express the extent to which a reaction will ionize, or the extent to which an acid will ionize. Weak acids don't ionize very much. We use K values to determine how one acid ionizes more than another acid, if they're both weak acids. So let's talk about these K values. They're called dissociation constants. So if we take a generalized acid dissociation, that's some acid, we'll call it HA. A is for acid. The H means it's a proton that could be donated. So a proton with an acid reacting with water. Dissociation happens in water. You put an acid in water, it dissociates, and you're expecting, according to Arrhenius, to get H plus in solution. So an acid dissociates in water, dissolves in water, and will dissociate into A minus, your conjugate base, and H3O plus, your conjugate acid. If I were to put this equation into an equilibrium expression, I get K sub A. K sub A is the equilibrium of a weak acid. A means acid. K sub A equals my products over reactants in terms of their concentrations. My products, A minus and H3O plus. My reactants, my acid, and my base, water. However, my base is in the liquid form, and we do not put that in our equilibrium expression, so we just have this for K sub A. Now, this K sub A constant is called your acid dissociation constant. It measures the extent to which an acid will dissociate in water. The greater the value of K sub A, the stronger the acid. Now, we can use different criteria to calculate Ka. We're going to learn how to do that now from pH. So, an example problem. The pH of a 0.10 molar solution of formic acid at 25 degrees Celsius is 2.38. Calculate the K sub A. The first thing we have to do is figure out what our chemical equation is. We started with formic acid. We know we're talking about dissociation. That's what K sub A is referring to. So it's going to be reacting with water. This is going to be my acid. That's my base. My acid donates a proton to my base, giving me HCOO1 minus and H3O plus. The proton that's given in formic acid is the proton connected to the oxygens here. You don't have to know that, but that's just why it's not this H, but it's this H. This is the donate. Sorry, it's not this H, but it's this H. This is the proton that's donated with formic acid based on the type of functional group that's there. We'll learn more about that later on. Now the question is asking to calculate Ka. To calculate K sub A, we have to put our reactants and products in our expression. And we get this, products over our reactant. Now these concentrations are concentrations at equilibrium. The question does not give us concentrations at equilibrium. It simply gives us an initial concentration of formic acid. Then it dissociates into equilibrium. So all we're really given is the initial concentration of formic acid. We have to make an ice chart here to calculate the concentrations at equilibrium. So we know we have 0.10 molar. It hasn't dissociated yet. This is what we originally start with. So we don't have any of our products yet because this weak acid has not dissociated yet. So we know this is going to dissociate, meaning diminish its concentration, and these will increase in their concentrations. Now, we are not given any other information about the concentration at equilibrium to figure out what the change is here. But we are given a pH. Something special to know about pH, or even just acid and base reactions in general, is that these reactions happen extremely quickly. So equilibrium is achieved very quickly, so quickly that when the pH is actually measured experimentally in laboratory, that reaction has already reached equilibrium. So you react, you go to get your meter, equilibrium has already happened. So you go and measure the pH. The pH you measure is based on your hydronium ion concentration, right? pH is equal to the negative log of hydronium. So this concentration that's measured through pH is already the concentration of H3O plus at equilibrium. So when you measure the pH, you're measuring the concentration of H3O plus at equilibrium. So we can use our pH here, 2.38, and calculate the H3O plus. And this will be the equilibrium concentration for that H3O plus, your hydronium. So let's do that. We input 2.38 for our pH. That equals negative log of H3O plus. Our variable here is the H3O plus concentration. This is not multiplication, so we cannot divide both sides by negative log. We have to do the inverse operation of a negative log, and that is applying a base 10. So you raise both sides as a power of 10. So 10, and I'm going to bring the negative over here as well, so I could just deal with log and not negative log. Bring the negative over here. So it's 10 to the negative 2.38 equals 10 to the negative, 10 to the positive. I took the negative and brought it over here already. So 10 to the log H3O plus. 10 and log, base 10 and log are inverses of one another. Thus, these two cancel. So I have 10 to the negative 2.38 equals the concentration of hydronium. You must simplify this, and you will get 4.2 times 10 to the negative third molar. That is your concentration at equilibrium for hydronium. So we know our change must have been 4.2 times 10 to the negative third for both. And since they're all in a 1-to-1 ratio, this is a monoprotic acid, my decrease was also the same. So at equilibrium, I have 0.10 minus 4.2 times 10 to the negative third. That's going to give you about 0.0958. Now be careful here. You don't want to round to sig figs, because if you round to sig figs, you're just going to get back to 0.01. So it appears as though nothing would have changed. Again, if you round this number to sig figs to, not round to sig figs. If you round to sig figs according to subtraction here, it would be basically to this place here, to 2 past the decimal. And that 5 would tell this 9 to round up to 0.1, and it would look like nothing's changed. But that is a significant observation. Weak acids don't dissociate very much. So at equilibrium, their concentration is really close to what it originally started with because, by definition, weak acids don't dissociate very much, especially this one. So now, that's my equilibrium concentration here. Here is 4.2 times 10 to the negative third, and 4.2 times 10 to the negative third. I can input this into my equilibrium expression. Case of A. 4.2 times 10 to the negative third. That's 4.2 times 10 to the negative third over 0.0958. And I get approximately 1.8 times 10 to the negative fourth as my case of A. So that is how you would calculate case of A from a pH and an initial concentration. One special note, the Ka for weak acids is usually between 10 to the negative second and 10 to the negative 10th. Now, there's another way to measure acidic strength. Really important for weak acids. And that is through something called percent ionization. Percent ionization is looking at the ratio of the concentration of your ionized substance in solution. We'll talk more about what that is, but what was ionized in solution in comparison to your original concentration, multiplied times 100. Now, a stronger acid will have a greater percent of ionization. For any acid, the concentration of acid that ionizes is equal to the concentration of H3O plus that forms. So your numerator, you'll always be looking at your concentration of H3O plus at equilibrium. So your percent ionization will be your concentration of hydronium at equilibrium divided by your initial concentration of your acid times 100. An example of that. If we have 0.035 molar solution of nitrous acid, it contains 3.7 times 10 to the negative third molar H3O plus at equilibrium. So I dissolve 0.035 molar nitrous acid in water. At equilibrium, it dissociates into 3.7 times 10 to the negative third molar hydronium. What is the percent ionization? So this one, fairly simple division problem. Here is my equation. The concentration of hydronium at equilibrium over the concentration of nitrous acid initially. Plug those values in, multiply times 100, and here we get 11%. We'll talk more about what this number means and also how to do the opposite of our last board. In our last board, we went from a pH to a case of A value. We can also go from a case of A value to a pH. Gentlemen, take notes. Adios.